So in our Foundation 1 lesson, we are going to be dealing with transformations, and I am going to start with a nice, simple one that we all know and all can deal with, and that is translations. Now, what are translations? Translations is really just about taking your shape and moving it. So you aren't changing the shape, you aren't changing the size, you aren't changing the orientation. It is exactly the same shape, just up or down or left or right. All right, so let me share my screen with you. And I want GeoGebra, there we go. All right, so I have drawn an L for you. Just so that we can check orientation, we can check size. It's a shape that we all know very well. And I hope you guys remember as well that I have the chat open there on the side. So if you have questions during, make sure you ask them. All right, so what I've done is I've created a base brownie orange shape, and then I've overlaid a pink shape over that we're going to be moving. All right, so if I want to move the shape vertically, and I have a vertical translation, we can see that the shape is now moving upwards. So if I, for example, move it 5 units upwards, we can see that every coordinate of the shape has been moved 5 units upwards. So for example, A was at 2, A is now at 7, and that is 1, 2, 3, 4, 5 units upwards. And we can check for every one of the other ones, it is 5 units upwards. Totally equivalently, we can see that this is exactly the same shape. It hasn't changed at all. And if we have a shift downwards, it's exactly the same. We can take A is currently at 2. A would then be there at -3, 1, 2, 3, 4, 5 units downwards. Once again, proving I have not changed the shape. There we go. Now that's our up and down translation. What about moving it side to side? Well, I can move it to the right, 5 units say, and if I take A is currently at 5, that's where A would be, it's now at 10. 1, 2, 3, 4, 5 units to the right. Moving it back, we can see we haven't changed it at all. Moving it there, there's where A would be, 5 down to 0, 1, 2, 3, 4, 5 units. So that's the 4 kinds of translations we could have. Now it's important to remember as well that we could also have more than one translation at the same time. So we might be able to move the shape, say 3 units upwards and maybe 2 units to the right. And that's what my shape would look like. So A is moving 3 units upwards, 1, 2, 3, up to that point there, and 2 units to the right, 1, 2, and that's exactly where we've ended up. So this can essentially move anywhere that we want. And then, just to once again prove that it's not changed at all, it totally overlaps. So that's your translations. Hopefully no one is struggling with translations. If you do, please send a message in the chat. All right, you guys are happy with that. Then we can move on to something a little bit more entertaining, and that is my reflecting. All right, so opening up my reflecting graph, and I'm going to share my screen and share with GeoGebra. All right. So remember, with reflections, you have a line of reflection, which essentially acts like a mirror. So if you look at a mirror, you see yourself. And however far away from the mirror you are is exactly how far the image in the mirror is from the mirror. So for ease, I'm going to call you, you, and then I'm going to call Mirrorland you, the person on the other side of the mirror, in Mirrorland. All right. So you have a shape. And even if you, I'm sure as you were younger, you would have taken your finger and you try and move your finger closer and closer and closer towards the mirror until you touch the mirror. And then you find that the finger on the other side of the mirror gets really, really, really close. You may have noticed that they never quite touch, but that's just because of the thickness of the mirror. And that's the idea of reflections. So the size of your shape will not change, but the orientation is going to change in a sense because it is mirrored or reflected over a line. So here we can take this shape as the original shape and this shape as my image in Mirrorland. If you have your finger pressed onto the mirror, that's point B, the image is going to be right there. If you have your finger further away, like point C, this is going to be further away, but they're going to be exactly the same distance away. You can see it's 1 block and almost 2, just as this one is 1 block and almost 2, the exact same difference between them. Same with D here, 1, 2, just over 3, 1, 2, just over 3. All right. Now, what happens if I move the original image further away from my line of reflection? Now we notice that this image seems to be further away as well. B, instead of being on the line, is now 1 block away. So 1 block away in real life is 1 block away in Mirrorland. And C is now further, is now 1, 2, and almost 3, 1, 2, and almost 3. So you can see that as we move the original image further away, the image in Mirrorland gets further away as well. And all of us can see that, and it's kind of an idea that you would know about. What creates a problem is when we start going the other way. Have a look at this. This creates a problem because now part of your image or part of your original value, your original object, is now leaning into Mirrorland. So if we were to have to draw this image here, that you would have to do in little bits, essentially. So, for example, initially, we could, if we wanted to draw this, we could take CB over there, reflect B to B dash, same point, reflect C to C dash, which is over there, join that line, and that's the reflection. If we bring it closer to here, we now have a problem because it might be a little confusing to join that whole line because there's where my line of reflection is. So I'm now going to have to join only this bit first. So it's C to the line and then reflect C and then join that bit first and then take B and reflect it to that side and create the rest of that line and then the rest of that line to the image. So we are now actually having to break it up into smaller pieces so that we still deal with what's on the one side of my reflection line and what's on the other side of my reflection line. And we can see that the further the reflection line goes, into my shape, the more I'm going to have to reflect in different bits. So here I've only got a tiny bit of the line, so a tiny bit, and here's far more of the line and far more of the line. And all of these lines over here are now reflecting to the left, not to the right, because they now sit on the right. Three. So here we have our reflection line, and we can now see that this, that was my original image, now is going to be reflected to the left-hand side, because we are no longer standing on the right looking into the mirror. We're no longer standing on the left looking into the mirror and seeing the reflection on the right. We are now standing on the right looking into the mirror, seeing the reflection on the left. This is when we show off our superpowers, and we can literally delve into Mirrorland, and then part of Mirrorland will come out to us. Any questions about this? All right. So all of you guys are happy with that, which is great news. And then we're going to do the last one. And the last one is the most interesting and the most fun to watch. All right, I'm going to reshare my screen again to GeoGebra. All right. So what I've done is I've again got my L shape, but we are now going to be rotating this L about points A, B, C, D, E, and F, just to show you how the different points of rotation is going to affect your shape and how the orientation is going to change. So once again, with rotations, the size is not going to change, but the orientation is very much going to change because it's being rotated. But how it changes is all dependent on your point of rotation. All right, so I am currently going to be reflecting about D. That is what is in motion at the moment. So if we rotate D, we can see D as the pivot point. So imagine putting like a tack or a thumb point or a thumbnail or something like that into a board at D, and then you just rotate it around. We can see it rotating through. And I will get it to 90. There we go. So that is a 90-degree rotation. And that rotation is happening clockwise. Then we can hit 180. There's 180. We hit 270, which is the equivalent of 90 degrees anti-clockwise. Oh, just missed 270. There we go. And then just to show you again that it's still the same, we can go all the way to 360. And we see that it's exactly the same shape. So there's a question that says, is this in our exams? Yes, most definitely yes. If it wasn't in the exams, I most likely wouldn't be teaching it to you. So this is very much in the notes. But again, in the notes, it's very difficult to take stagnant shapes and get the idea of what is actually happening to them. So that's why I'm doing this, because this can literally show you how it's turning. All right. If we want to take it around, let's say point B, because point B is also quite interesting. So there's my shape, and I rotate it. Now we notice this is very different to how it was with point D. So this is your 90 degrees. Here's coming up your 180 degrees. There's your 180. We keep going around. We hit 270, or of course 90 degrees the other way. And then we keep going around, 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 around. And we see that's exactly the same shape. All right. Another very good question that's come through. How do we do this without this app? Are there set coordinates? So yes, there are set rules on how to do rotations. Most of the time, you will be required to rotate about the origin. So I'm specifically not using set coordinates or rules because you're going to be using it about the origin, and that has a set rule. All I'm trying to get you to see is how things are meant to be moving. Because if you can start visualizing what's going to happen, it is far easier for you to actually be able to do it and not have to worry about just learning the rule and applying the rule. You'll literally just be able to see it and do it. All right, let's do one more. I think E is also quite a nice, interesting point. And then what I'll do is I'm going to put all of them on, and you'll see how all of them are different to each other. All right, there you can see it turning. There's the 90. I hope you guys also know that you guys will only ever have to worry about the 90, 180, and 270 rotations. You'll never be given a random like 132 degrees. You don't need to worry about that. All right, there's my 270. And then again, all the way around to 360. All right, so let us now engage all of the shapes. So I'm going to have my stock standard L that doesn't move to show you as a reference. I've engaged C, I've engaged E, I've engaged A, I've engaged B, I've engaged D, and F. All right. So now, as we move along, you can see this looks rather cool. Let's get my 270, there we go. So you can see that this purple shape is rotated about A. The blue shape is rotated about F. The green shape rotated about E. This kind of pinky shape there is about D. The brown shape at the bottom is by C. The red shape over there is by B. And then this over there is my original L. D shape is magenta. Thank you, I do appreciate that. It is indeed magenta. Someone knows about printer cartridges or is really good at color and painting. All right, here's 180. There's 180. Fantastic. We can see all of them are now still completely different. Interesting, if you have a look though, is each of these that are being rotated, you could actually get from one to the other using a translation, being the shifting. So this one is shifting 2 units to the right. There you'd be shifting a couple units down. 1, 2, 3, 4, 5, 6, 7, 8 units down. this one to there, 1, 2, 3, 4, 5, 6 units to the right, 2 units upwards. From here, 1, 2, 3, 4 units to the right. So that's also a very interesting idea, how translation comes into rotation. And we see they come around, they start lining up very nicely and neatly. Again, all of these are the same shape, same size, and same orientation, but still different to the original brown one there. And then they all fold nicely and neatly back onto the original, which is really cool. So that is what rotation is. And that's why it's important that when you specify rotation, you don't just specify a number of degrees or a direction, clockwise, anti-clockwise. You need to specify about what point it is being rotated. Unless it is specified in the question, you need to mention this.